Good afternoon, everybody, and welcome to today's Congressional Neuroscience Caucus briefing, Inventing the Future, Brain-Inspired Next-Generation Artificial Intelligence. So I'm Mark Resnick. I'm chair of the American Brain Coalition, and I'm a neuroscientist. I'm a professor of physiology and psychiatry at the University of Illinois, and a research career scientist at the Jesse Brown VA in Chicago. So the American Brain Coalition, in partnership with the American Academy of Neurology, is that on? It's on. We can hear, right? It's a little room. The ABC, in conjunction with the American Academy of Neurology, American College of Neuropsychopharmacology, Simons Foundation, Society for Neuroscience, is proud to host today's event for the Congressional Neuroscience Caucus. Before I welcome Dr. Natalia Rost, who is president of the American Academy of Neurology, I'd like to first recognize the Congressional Neuroscience Caucus, our host for today's program. And we're, unfortunately, Mike Thompson from California, a co-chair of the caucus, is unable to be here today, but we have our other co-chair here, Congressman Morgan Luttrell from the Texas 8th District. Congressman Luttrell is serving in his second term. He's a former Navy SEAL, and he survived a 2009 helicopter crash that left him with a traumatic brain injury, an experience that deepened his commitment to neuroscience and to recovery research. After military service, he earned a graduate degree at the Applied Cognition and Neuroscience from the University of Texas, Dallas, and today he works to support fellow veterans suffering from traumatic brain injury and PTSD. Congressman.
Gentle on the fingers, I got you. Hello, everyone. Good afternoon. It's always a privilege to sit down in front of such the brilliant minds that work in the neuroscience space. Works in the neuroscience space, you know, and I often say when I'm standing in front of, I like to say, my colleagues that speak the language that most of us don't speak and understand because it's such a dynamic language that continuously changes. But here we are. When we discuss issues of the brain and brain health, brain disease, cognitive disorders, it's often lost in translations to those that we try to communicate with because we're still trying to figure out how this beautiful substance between our ears actually works. And that's where you come in. As hard as we push, and I constantly talk to my colleagues that, you know, come up here and see me any chance they get, and when I'm traveling around my district and talking to the subject matter experts, you know, you can never shove hard enough. You can never push hard enough to figure out the answer to this unknown space that we're traveling through. And as science and technology and medicine converge, it becomes even more challenging, because we have these cross-functional dynamics where languages are now not speaking to each other. But there's an opportunity there, I think, that if we continue to run shoulder to shoulder, and I don't mind if I have to say the word break down silos and sow the seams again between academics, I'll say it one more time, but the silos that live and breathe inside of our academic institutions and our medical space have to go away. You know, information sharing is absolute. And today we're going to talk about artificial intelligence and how the progression of AI and technology is living and breathing everywhere. It touches every aspect of almost human existence, it seems like. At least at my position at the congressional level, it seems like AI is too abundant. Anyway, so where do we sit? Where do we stand? And where are we going? Now, the scans that Ms. Murder was actually showing me, you know, the advancements in artificial intelligence will pave a pathway for us that, you know, we don't have that capacity. We need the computational systems to jump in on top of this and analyze that data that we've been aggregating for decades and decades and decades and decades. We have such a rich data set. And we ask these questions But if you put all of us in a room together like this and put a computer in front of us, it would take us hundreds of thousands of years to solve a simple problem. Okay, now introduce artificial intelligence. Now the trick is a data scientist doesn't speak what you speak. They don't understand that language. And I constantly have these conversations with we need to come together and figure that out. How do we utilize the ones and zeros to solve the problem that lives between our ears? Somebody argue that against what I'm saying, but I think it's time to say, okay, this is where we are. Now, as a member of Congress, and everybody, I've had a conversation with a lot of you in here, and frustrations live because you can't do what you need to do unless you have the ability to do so. You want it, you're hungry, and here comes the funding lines and with the dollar bills that live on top of us. I got it. That's my job. There's one of me up here that speaks the language of neuroscience, and I have to explain brain health, brain awareness, cognitive issues. I have to explain that. And when I was in grad school and my professor was teaching me, I said, hey, look, can you put that in crayon for me? I have no idea what you're saying. And I'm not taking any away from the congressional members. They're all brilliant minds, but this is a very hard subject to grasp. But I'm utilizing everything that you ask for through me to get to them in order to help us out. And it's a challenge, okay? Now, as we utilize artificial intelligence and neuroscience, and you guys are chipping away at the problem sets, again, when I say cross-functional team, and it takes you, it takes everyone else, it takes me, and it takes the understanding for us to get to the next phase of evolution. Fair enough? And I'll continue to do so while I'm here. The only thing that I ask, and I'm going back kind of into my Navy SEAL days, you got to get up every morning, no matter how many times you fail, no matter how many times you get hit in the face, you got to get up the next morning, and you got to do it again. Because there's not that many of you. There's not. And everybody else is counting on you. And they're not going to tell you to your face. They're not going to thank you. They're not going to tell you to keep going because they have no idea what you do. I do. And that's why I'm telling you. You got to keep going. Every time you get hit to it, you got to stand back up. You got to take your legs, and you got to keep going. Because one day we'll figure this out. One day we will. And every single thing that you've done adds to that. And as we keep putting this puzzle together, it will happen. And I hope it happens before the day that I die, but the good Lord has a pathway for everybody. So with that, I'll turn it back over to this amazing group, and I want to thank everybody for coming up here and letting me kind of, it's good to offload to people that understand exactly what I'm saying. You'd be surprised when I'm talking to members of Congress, they're just kind of looking at me with this look on their face, like you see them on TV, they don't have any idea what's going on. And, but thank you. And God bless. And I'll turn you loose.
Good afternoon, everybody. I'm Dr. Natalia Rost, President of the American Academy of Neurology, and it is my great pleasure to join you here at the 2025 Neuroscience Caucus briefing. I'm here on behalf of more than 40,000 of neurologists and neuroscience professionals to support this caucus in shining spotlight on the critical role of brain health and neuroscience research. Advancing research is essential, not only for understanding how the brain works and to treat neurological disorders, but also for improving quality of life across the lifespan. And the American Academy of Neurology has made a commitment to brain health through our Brain Health Initiative, which focuses on accelerating scientific discovery, optimizing patient care, and engaging the public and policymakers. Because together, we can ensure that neuroscience research continues to receive the attention and the resources it deserves. I wanted to thank Katie Sales for the amazing work that she does for the American Brain Coalition, as well as our colleagues at the Society for Neuroscience and the College of Neuropsychopharmacology. I'd also like to thank the Congressman and Congressman Thompson, who is not here with us, but they are co-chairs of this caucus, and we thank you greatly for putting together this great event. And now it's my great pleasure to welcome and introduce our keynote speaker for today's briefing, former Congresswoman Jennifer Wexton. As many of you know, Please, round of applause. As many of you know, Congresswoman Wexton served Virginia's 10th district right here in the U.S. House of Representatives from 2019 to 2025, where she quickly became a tireless advocate for science, research, and public health. Her dedication to brain health and neurological research, informed by her own lived experience, has left a lasting impact, not just on policy, but on the lives of patients and families across this country. During her time in Congress, she was a driving force behind the bipartisan Healthy Brains Act, legislation that seeks to bolster research into environmental risk factors of neurodegenerative diseases such as Parkinson's disease, atypical Parkinsonian disorders, Alzheimer's disease, ALS, and MS. This legislation elevates the national conversation on brain health and would catalyze research into the environmental risks for neurodegenerative diseases. The Congresswoman has also put together an instrumental package in the passage of the National Plan to End Parkinson's Act, a bipartisan effort to develop a coordinated, whole-of-government response to Parkinson's disease. This legislation marked the first federal bill dedicated to ending Parkinson's disease and was a landmark success for the brain health community. Her work has helped ensure that the voices of patients, caregivers, scientists, and advocates are heard at the highest levels of government, and her legacy continues to shape how we think about and invest in the future of neuroscience. Please join me in welcoming a true champion for the brain health community, former Congresswoman Jennifer Wexton.
Hello, it's great to be here with you today. I want to thank the Congressional Neurological Caucus for inviting me to share my story. For those of you who may not know me, I'm Congresswoman Jennifer Wexton. I served in Congress for 6 years before my retirement in January. 2 years ago, I was diagnosed with progressive supranuclear palsy, or PSP. I describe it as Parkinson's disease on steroids. PSP has severely impacted my mobility and my ability to communicate verbally. That's why I now rely on this impressive AI recreation of my voice, not only for public speaking engagements like this one, I also use it when I'm home talking with my family and anytime I want to be understood. Before my ordeal with PSP began, the most I engaged with the idea of brain health was playing the New York Times games, something I still do daily. I kept up relatively well with my physical health, running regularly, training for races, going to the women's gym in Rayburn, and taking group fitness classes, especially yoga, strength training, and pre-pandemic, I was a regular at the 6:15 a.m. spinning classes in the main gym. Fun fact, that's where I met Mike Thompson. I did and do eat healthy, and I avoided unhealthy habits. I never missed my annual physicals with my primary care physician, and other than maybe needing to lose a few pounds, I believed that I was in excellent health. What I had not anticipated were the invisible ways that my brain wasn't healthy and how it could so quickly and severely impact my overall health and well-being. With the benefit of hindsight, I realized that I first began experiencing noticeable symptoms of PSP in 2019. My toes would clench up and curl inward. I explained it away as the natural result of my walking tens of thousands of steps on the marble floors in and around the Capitol complex daily, often in less than supportive shoes. As the months passed, my gait became more of a shuffle, and I would often hit the toe box of my shoes on uneven sidewalks in Capitol Hill. And believe me, there are a lot of uneven sidewalks in Capitol Hill. I had never been particularly graceful, so even then I explained it away as my being lazy and not picking my feet up enough when I was walking. In 2020, 2 more symptoms manifested themselves. The first was the onset of dystonia in my hands, which would ball into fists involuntarily. I remember going for a walk with my husband when he noticed my fists. He said, "Ooh, I'm so angry," and balled his own hands into fists, imitating my body language. I laughed and made a conscious effort to relax my hands, but I noticed that my arms didn't swing like they used to. Postural rigidity, I came to learn, is a common symptom of Parkinson's and certain atypical Parkinsonisms. The second and more disturbing symptom was a change in my voice. I had been doing a lot of virtual town halls on Zoom on various topics, and I remember one time that my voice started wavering. It was as if I were very scared or freezing cold and shivering. Of course, it freaked me out, and being freaked out definitely doesn't help when you're experiencing an issue like that with your voice. It wasn't until later, when I noticed that I had trouble speaking slowly or with sufficient volume to be heard or understood from more than a few feet away, that I finally had enough sense to Google my symptoms. I typed, "Why do my toes keep clenching and curling in?" into the Google search window. The answer, Toes clenching is a common symptom of early onset Parkinson's disease. I was incredulous. I thought, I can't have Parkinson's. I hope that's a disease that old men get. But the more I read about it, the more all of my recent maladies made sense. And I knew they were all symptoms of PD. I made myself an appointment with my primary care doctor. Then it took me almost 4 months to get an initial appointment with a neurologist, and it was virtual. My second appointment took place about 6 weeks after that. What followed was a continuing pattern of my neurologist prescribing me a new medication, increasing the dose until I was taking the maximum recommended dosage, and my experiencing little to no benefit until she finally decided to break out the good stuff: carbidopa, levodopa. It was amazing. I took 1/2 of a generic Cinemet tablet, and it was as if all of the angels in heaven started singing hallelujah just for me. For the first time in many, many months, my clenched, dystonic muscles finally started to relax. I remember thinking, why didn't my doctor let me try this sooner? It also felt good because my body's robust response to Cinemet finally validated my Parkinson's diagnosis, or so I believed. I announced my diagnosis to the public on April 12th, 2023, on World Parkinson's Day, in a video message where I vowed to put in the work to manage my symptoms and continue doing the job I loved of representing my community in Congress. I embarked on a reinvigorated exercise routine to help manage my Parkinson's symptoms. While I was still able to move and run at the time, I had already begun noticing the ways that my medications weren't working as well as they used to, and it seemed that my symptoms were progressing more rapidly than those of others I knew with Parkinson's. By this point, I knew well the importance of listening to my body and sought out a second and a third medical opinion. After an impromptu cursory exam by a neurologist I happened to be meeting with in my Capitol Hill office, an additional examination of an earlier MRI, it became clear, the telltale sign of midbrain atrophy in the shape of a hummingbird on my MRI scan, that I was battling the tauopathy, PSP, a much more severe and faster progressing form of atypical Parkinsonism. PSP has no known cure and minimally effective treatment options. My diagnosis journey took the course of more than 3 years, months of trying different medications, slowly ruling out a handful of other diseases, opinion after opinion, test after test. And every step of the way, through no fault of the incredible medical support I received, I was left with frustratingly few answers to the most important questions that every person asks when going through an ordeal like this. What is wrong with me? Where did this come from? Why me? And how can I get better? Although I have my suspicions, I will never know for sure if my PSP came from some rogue gene in my chromosomes or was due to exposure to some toxin or something else entirely. And although I've gotten my hopes up on more than one occasion after hearing about this or that miracle drug that was in the clinical trial stage, I've seen enough to know that no medication or treatment regimen available right now is going to make it go away. While I've been asking myself these and many other questions for over 2 years now, there is one answer which has presented itself loudly and clearly: we need to do better. More than 50 million people worldwide suffer from neurodegenerative diseases like Parkinson's, ALS, Alzheimer's, MS, or conditions like my PSP. And that number is growing rapidly every day. And yet so many of the questions I had are shared by those 50 million people. We need to do better to step up our fight against neurodegenerative diseases. That's why I've made it my mission over the past 2 years. I recognize the unique position I had as a member, and now as a former member, of Congress and the spotlight I had on me, and I wanted to make the most of it. I have used my personal story to bring about important change. Last year, I was proud to champion the National Plan to End Parkinson's Act, a bipartisan historic piece of legislation which aims to build a national plan to prevent, treat, and eradicate Parkinson's disease, including atypical Parkinsonisms like my PSP. We certainly encountered some bumps in the road with this bill. In fact, the bill very nearly died before it got a vote on the House floor, as many bills do, as a casualty of a proxy battle between Republicans and Democrats over a culture war issue. But I was not afraid to pull on the heartstrings to bring people back together around this bill. I shamelessly and sincerely played the "I'm dying, and this bill is a top priority for me" card. Colleagues on both sides of the aisle responded with words of comfort and encouragement, and most important, with a commitment to take action. What I found most surprising was that as I shared my personal struggle in support of the national plan, my colleagues frequently confided similar stories about a relative, parent, or friend who had faced or was facing a similar battle. I should not have been surprised, as Parkinson's disease is now the fastest growing neurodegenerative disease in America. Seeing what the people close to them had gone through, and the frustration of not having the answer to those same questions I asked myself in the aftermath of my diagnosis, motivated them not to walk away from this life-changing legislation, and they helped us successfully pass it through the House and Senate. I proudly joined President Joe Biden in the Oval Office for the bill signing, and it was a special moment. I've lived in the DC region my entire life, so getting my White House moment like that, especially surrounded by my family, meant so much. It was certainly not the circumstances I anticipated, relying on a walker and using text-to-speech technology to share my gratitude with the president. But to put the icing on the cake of that day, my team and I had been working with 11 labs on developing my new AI voice, and it was ready just in time for the White House event. The first time I used this remarkable recreation of my new and old voice was to speak with the president at the signing of the national plan. As I set out to use my platform in Congress to fight for better brain health, I didn't fully anticipate what my platform could mean, not in terms of votes and policy, but in visibility. I have always been the kind of legislator who would much rather put her head down and get into the work rather than spend my time in front of a CNN cameras or going viral for some stunt or another. It was in that spirit that I entirely underestimated what would happen when I first used my text-to-speech app with its bare-bones, robotic-sounding voice on the House floor. Evidently, it was a history-making moment. For me, I was simply trying to get one of my bills passed, a bill renaming the Purcellville Post Office after one of my favorite part-time constituents, former Secretary of State Madeleine Albright. My motivation behind using the text-to-speech tech was doing anything I could to keep doing my job. Yet, it turned into what I have to believe is one of the most watched post office renaming speeches in a long time. After making history as the first person to use augmentative and alternative tech on the House floor, I received a great deal of attention in the press and, more meaningfully, an outpouring of supportive messages from disability rights advocates and people facing similar health challenges from all across the country, again, catching me off guard. I didn't anticipate that kind of attention because I've been used to being in public view, as I've spent over 2 decades in public service. And my entire health battle with PSP has been in the public eye. But for the majority of PSP patients and many others facing neurodegenerative conditions, these diseases push you not into the spotlight, but into isolation. PSP is a lonely disease. It robs you of your mobility, being able to walk, run, dance, travel under your own power, and even worse, your ability to communicate by speaking. I don't bemoan the ways my health struggle has become very public. Rather, I see the privilege I have in it and recognize the opportunity it offers. I had the luxury of my team from my congressional office helping me get around to votes and other official commitments and scheduling my day. And while I no longer have a staff, my husband and caregiver, Andrew, manages to get me up and out in time for my many appointments. I had years of old voice recordings from public appearances, which made it possible for 11 labs to develop a scary good AI recreation of my voice, giving me back something which I thought I'd never hear again. With my new, old voice, I have the platform and the means to tell my story on my terms. I recognize my privilege and I recognize the power in that, and I've tried to make the most of it. I've shared the ways PSP has affected my day-to-day life and what this disease is and is not. I've politely but firmly corrected my colleagues who have come up to me and spoken to me as if I were a child, mistaking my physical decline for a mental one. I've encouraged other PSP patients to do things that can help them along their journeys, like recording their voice so they too might be able to develop an AI model and keep their voice. I've shared my story in every way that I can because I hope that it makes this struggle just a little less lonely and isolating for someone else going through what I am. For that reason, I'm going to keep up my advocacy. Shortly after I first used my text-to-speech assistive tech on the House floor, I received a text from one of my former colleagues in the Virginia General Assembly, which read, "I know that you always do this work for all of us, but I want you to know that my friends who have littles that use assistive technology have reached out to tell me that not only have they shown their kids your speech yesterday so that now they can see someone who talks like them, but they all feel that the light you shed on assistive technology will likely do more to advance it than you will ever know. So, while you're kicking ass for everyone, you kind of just changed the world for a lot of my favorite kiddos. So proud to know you." Reading those words meant so much to me, and they still do today. I don't say any of this to brag. My hope is that I can make the most good out of this admittedly awful situation as I can. As I move forward, I hope that I have and can continue to help bring greater resources towards answering those impossible questions that a diagnosis of a neurodegenerative condition like my PSP brings, and to give people going through these struggles more courage and comfort to move past those questions and fight their own battles with these horrible diseases. Because for me, the best way out is always through. I'm so grateful for the work that so many have done to help better diagnose, treat, cure, and prevent these neurological conditions and the comfort you bring to those fighting them. To know that there are such brilliant, determined, and caring people who have dedicated their careers to this cause means the world to someone like me. So thank you, and thank you for the very kind invitation to join you today. As I've said, sharing my story is a power I have right now, which I believe is far greater than the power of my vote in Congress ever was. Thank you for allowing me to share that story today.
Thank you, Representative Wexton. Thank you for your leadership on Capitol Hill, as well as your courage and leadership in navigating this next phase of your life, living with PSP. You're a true inspiration to us. And now I'd like to turn over to Dr. John Nye, Director of the NIH Brain Initiative, who will moderate today's panel. Dr. Nye.
Thank you, Dr. Roast. Hard to follow such an inspiration from the former Congresswoman. I'd like to thank all of you for being here, the Congressional Neuroscience Caucus for hosting American Brain Coalition, the AAN, and for your interest in how we can not only use AI to advance neuroscience, but as I hope you'll hear about today, how we can use neuroscience to advance AI. So I'm John Nye, I'm the director of the NIH Brain Initiative. Our mission is to revolutionize the study of the nervous system by developing new tools and technologies, both for basic discovery and also to advance health. So 1 in 3 Americans is living with some disorder of the nervous system. 1 in 3, over 100 million people. I would wager that everybody in this room either is living with some disorder or has a close friend or family member who is living with a disorder. It affects all of us. And cures cannot come soon enough. But the issue is that it's the brain's complexity. So it's composed of a couple 100 billion cells, about 100 billion neurons, nerve cells. To put that in perspective, that's about as many stars as we think are in the Milky Way. Incredible complexity. They make hundreds of trillions of connections. And it's the most complex organ in our bodies, and it's also, I would argue, the most powerful and flexible and energy-efficient computer known to humankind. And we're going to come back to that because we're going to take some lessons from that to build better ways of inventing new computers and AI. So understanding how our brains underpin all that make us human and also different as individuals, based on our senses, our emotions, our unique personalities, consciousness, the ability to think about the future and remember events in the past. And what goes wrong in disease is the challenge of our lifetime. And it comes down to not just a great puzzle that needs to be solved, and I think that's what makes us unique as humans, this curiosity, but also you just can't fix what you don't understand, right? So we really need to understand how the brain works, and that's the motivation behind the Brain Initiative, many thousands of scientists that we support it, and also that NIH supports. Okay, so that brings us to the topic of neuroscience and artificial intelligence, or AI. As I'm sure everybody appreciates, AI tools are changing every aspect of just about every aspect of everyday life. It helps relieve us of the burden of mundane tasks, and we can get around to doing more creative and more important things to us. But it's also fueling scientific research and healthcare in so many different important ways. We just heard an amazing experience from former Congresswoman Wexton about how this has allowed her to communicate and still be effective as an advocate for the American people, but also to be able to communicate with her loved ones at home. It's helping scientists make sense of huge data sets. We're going to be hearing about that as well. It's assisting researchers design new drugs. It's helping doctors in the clinic deal with time-consuming office work so they can actually get on to the real task of what they're trained for, which is to take care of their patients. But there's really so much more that AI can do for us, not to replace us, but to make us better at what we do and to allow us really to reach our full creative potential. So I'll give one example. I had a really great graduate student about 25 years ago, and his project was to sequence a piece of genomic DNA that was about, well, this is technical, 100,000 bases out of 10 out of a billion, so 0.01% of the genome. Really smart guy. Took him a couple years to generate the data using then state-of-the-art technologies, and then maybe half a year or so, maybe a year, to kind of put it all together and publish a nice paper. He could have collected all those data in about a day, okay, and spent the rest of his 5 years dreaming up the next set of experiments and the next. And that's where we are today, which is using these new ways of approaching these massive data sets to dream up of new ways of analyzing complex systems like the brain of all animals, especially the human brain. So helping us understand the complexity of the brain, AI is really the big promise for the future, and we're going to hear about that, to help people live better lives, to live fuller lives, as we just heard from the former Congresswoman. And as we understand more about how the brain works, in what I call a virtuous cycle, this will inform the next generation of AI technologies. So it's not just a one-way street. It's not just about inventing new AI tools to understand the marvelous complexity of what's between our ears, but to then use that knowledge in turn to drive better, safer, more ethical applications of these AI technologies. So I would argue that the US staying at the forefront of these technologies is really critical for delivering them to improve lives for all Americans. And I would just say nobody does it better than we do it. Nobody does it better, I think, as that song goes. And it's also, therefore, an issue of national security. If we don't do it, somebody else is going to do it. So we have this really amazing panel of experts here that you're going to hear from. And as Congresswoman Luttrell said, we have people from different walks of life. Let's see, a neurologist, a computer scientist, a biologist, and a psychiatrist walk into a bar. And this is what you see. And you're going to see this great conversation, I think, between them. And I hope by hearing their perspectives, their stories, their passion for what they do, I hope you take away 3 main points. That understanding the vast complexity of the human brain is going to require the invention of more powerful AI technologies. There's no way we're going to get to it by just pounding away at it the way we've been doing it all along. And these AI technologies, second, will continue to push the envelope for how we can make people's lives better. And then finally, the last point I'll make is that understanding the basis of natural intelligence is going to deliver to us, has the potential to deliver to us better artificial intelligence to overcome the many limitations. And we'll hear about from the experts what those limitations are. So this is the emerging field of what's referred to as neuro-AI or brain-inspired AI. And that's the topic of today's panel. So I'm going to sit down and introduce our expert panelists. So I will turn on the microphone. Is it on? Is it on? Yeah. Oh, great. Okay. Technology, right? The first panelist I'll introduce is Dr. Lee Hochberg. He is a neurologist at the Mass General Hospital. He specializes in taking care of very sick patients. I think you were in the ICU over the weekend, so you look pretty good. I hope things went well for your patients. And he's also a biomedical engineer who co-founded what's known as the BrainGate Consortium, which he's going to tell you about. And he pioneered the development of so-called brain-computer interfaces, literally having a computer interface with the brains of people. And he pioneered the use of these brain-computer interfaces for life-altering technologies for patients, for individuals, for example, who are paralyzed from stroke, spinal cord injury, degenerative conditions like ALS, or as you saw here for PSP, to allow them to communicate with loved ones or to move limbs that they might have lost use of. So this was literally science fiction 10 years ago. I thought you guys are crazy to even think about doing what you're doing. But Lee, please just tell us about your background and how it motivated your work and some of the really amazing AI technologies that you guys employed that really just broke through in the last few years that really are giving people the hope of having a more normal life. I'll share. Okay. Go ahead.
That's yours. Thanks very much, John. And we are on a first name basis today, is that right? Just that good reality check. Okay. It's really a pleasure to be here. And I will just note, I see a few people standing there, some seats in the front, if you want to come forward. So as mentioned, I'm Lee Hochberg. I'm a vascular and critical care neurologist at Massachusetts General Hospital and Harvard Medical School, where I direct the Center for Neurotechnology and Neurorecovery, also professor of engineering and brain science at Brown University, and also I'm associate director of the Center for Neurorestoration Neurotechnology at the Department of Veterans Affairs in Providence, Rhode Island. So important disclaimer, which I think everybody in the room just said out loud, but I'll say it. None of my comments today represent the official policy of the Department of Veterans Affairs or any other federal agency. My words are only my own. Having said that, the one unifying activity across those institutions is, as John mentioned, the development of implantable brain-computer interfaces with the hope of restoring communication, mobility, and independence for people with paralysis, for people with cervical spinal cord injury, from brainstem stroke, from neurodegenerative diseases such as ALS, perhaps such as PSP, and others. And really one of the key advances in just the past few years of these implantable brain-computer interfaces, which I'll tell you a little bit more about, is the use of AI. So in short form, what is an implantable brain-computer interface? It's a device that's placed in or on or around the brain that records neural activity, that records some of these couple 100 billion brain cells. And they're recording in particular parts of the brain with the hope of serving a particular function. For example, if somebody's unable to move their own hand, we would place one of these devices in an area that's typically responsible for control of that hand. We'd record the brain activity, we'd listen in on those brain cells, if you will. And then with that neural activity kind of in hand, we'd decode that brain activity. And this is where the math appears. This is now where the AI appears, hoping that if somebody thinks about using their hand and we know what their brain activity is doing, that we can convert that intent back into action. We can allow somebody to control a cursor on a computer screen simply by thinking about the movement of their own hand and any number of other activities that maybe we'll get a chance to talk about. I think one of the places where AI has just been so helpful is that the earliest part of the 20 years that led up to where we are today, we began with basic kind of understanding of the brain, with a fundamental estimate of what that part of the brain is doing, and then we kind of build a map between that intent and that activity. But now, rather than having to use our guess for what that part of the brain is doing, we can use AI. We can use, and sitting next to experts, and we'll describe that in just a moment. But we don't necessarily have to go in with a hypothesis. We can say, we have data, and we know what the goal of those data are. Let's build a map. Let's use the power of AI to build that map, and therefore to be able to restore communication, to restore mobility, to be able to help people with neurologic injury or disease. And I'm really excited about the moment where we are.
Thanks very much. And there's so many different aspects of this story that we're going to get into as we go further along. So the next panelist I'd like to introduce is Dr. Alex Liao, who is a psychiatrist and a medical scientist, physician scientist. And Dr. Liao designed a simple yet ingenious iPhone app that's kind of like you can call it a Fitbit for the brain, as it's been described to me. It opens the door for widespread access to technology. One of the big challenges we have in medicine, biomedicine, especially neuroscience and behavioral sciences, is access to the latest technologies that can help people to help them lead healthier lives. So Dr. Liao, also Alex, has a very unusual background, not just as a trained physician and psychiatrist, but also in mathematics and as a concert pianist. And as I think we'll hear, all these things, it makes sense that they come together in this amazing creativity. So please, Alex, tell us about your background in medicine, mathematics, and music, and how that led you to dream up this invention of yours, and how it's helping not just people out there living their daily lives, but also how it advances your research with behavioral disorders.
Thank you so much for that introduction. I don't think that I'm a concert pianist, but I wanted to be a concert pianist growing up.
Not what I heard. Not what I heard.
I've heard Alex.
Not what I heard.
She is.
So I'm Alex, and I'm a professor in psychiatry, biomedical engineering, and computer science at the University of Illinois. And I am trained as a psychiatrist and also an applied mathematician. And I call myself a neuroscientist as well. So what we do is we build AI systems on our smartphones to understand how everyday activities, everyday behavior, everyday thoughts, how they come together to shape our mental health and our brain health so that we can take better control of our well-being. And I'm going to tell you how we managed to do that. If you remember back in 2015, that's when we started having things like Fitbit and Apple Watch. And I was so inspired by this idea of having a fitness tracker for the human body. But as a psychiatrist, I asked myself, if we can have a fitness tracker for the human body, why can't we have a fitness tracker for the human brain? As a psychiatrist, my primary population is bipolar disorder. I treat people with bipolar disorder, also known as manic depression. And when I see my patients in my office, a lot of times they don't necessarily feel comfortable sharing with me their darkest feelings. And even if they feel comfortable, they may not be able to evaluate their feelings objectively, or they simply forgot how they were feeling last week. Moreover, they come to see me once or twice a month, but they live with their symptoms 24/7. So having a brain fitness tracker can address these limitations. But how are we going to turn our smartphones into brain fitness trackers? And this is where the piano comes into play. Although I was never good enough to be a concert pianist, I take my non-existent piano career very seriously. I practice every day as much as I can. And every time I'm playing the piano, I'm always noticing that how well I can play the piano is dependent on my mood and my concentration for that day. So one day, as I was playing the piano, I realized that we should, of course, look into the keyboard on our smartphone. Piano has a keyboard, smartphone has a keyboard. To give you an example, what that means, imagine as I'm talking to you right now, also start texting a friend of mine at the same time, because my attention's divided, my typing rhythm will be variable, and I'll be having a lot of typos. If you can see my typos, I'll be using the backspace to correct my typos. And I'll give you another example. Imagine a person with bipolar disorder. This person has been recently using their phone at 3 a.m. at night and in an upright orientation. That means they're not even using their phone in bed. That means this person is most likely having a manic episode. So with this intuition, we decided to make our own smartphone keyboard, and we put the keyboard on the App Store for everyone to use. If you download the app from the App Store, you can set the keyboard to be the default keyboard. Then every time you are texting someone, writing an email, posting on social media, the metadata of each key press will be saved. So we can use mathematical models and AI to essentially conduct neuropsychological testing without having to talk to a person. I'm going to stop here. Thank you.
Thanks, that's amazing. Again, it's just this brilliant application. Well, identifying the opportunity in a way that perhaps somebody without your background wouldn't have. Well, they didn't because it didn't happen before. But really to help people who are out there living their everyday lives and being able also to help you as a psychiatrist with their conditions. So we'll get more into that. So we're going to switch gears a little bit, but I think it'll all come together. Our next panelist is Dr. Mala Murthy, who is a professor at Princeton University and director of the Princeton Neuroscience Institute, which is renowned for its amazing innovative science for driving neuroscience research with a pretty cool technology and theory bent. Mala and her colleagues have been at the forefront in using a variety of technologies to tease apart how the circuits in our brain really process information, receive sensory information, and govern behaviors. And Mala's work really embodies one of the key ethoses of the Brain Initiative, which is to think big, start small, and scale fast. And as I think you'll see, her work has been at the forefront in understanding the neural circuits that drive different behaviors. And the thinking, that's the thinking big part. The starting small part was she and her colleagues just revealed a complete connectivity map, not of a human brain, we're not there yet, but of the tiny and mighty little fruit fly. And I think, as we'll see as we go along, about how that's not only informing the science, but also the technology of everything that we're driving at to tease apart these circuits that are involved in all these different behaviors, but also in disorders. So Mala, if you can just tell us, what motivates you as a neuroscientist, what's your passion here, and how neurocircuits govern complex behaviors. And people will probably be wondering, after what I just said, how does the brain of a tiny fruit fly tell us anything about how our own brains work?
I get asked that a lot.
Yeah.
Well, it's great to be here. Thank you, John. Thanks to all of you for coming. I'm Mala Murthy. As John said, I'm director of the Princeton Neuroscience Institute. I've also been a professor at Princeton for about 15 years. And my lab indeed studies fruit flies. They have tiny brains, but they actually are capable of very interesting behaviors. They can form memories, they can make decisions, they can forage for food, they participate in social interactions, and of course they can fly. So pretty incredible little brains. Most people don't realize they have social lives, but actually social communication is the behavior we choose to study in my lab. Male flies actually sing these elaborate songs to females, and we use these behaviors to understand how the brain works. Well, about 7 years ago, it became obvious to me and others that we really needed a map of this brain if we were going to understand how it works. Just like you need a map to navigate around a new city, you need a map of a brain, all of the neurons, all of the connections to understand how it works. But at that time, for any complex brain, we didn't have any such complete map. And so my colleagues and I set about on this project, entirely funded through the NIH Brain Initiative, and it spanned several years to generate the first, what we call a connectome, or a brain map, for any complex brain, and that was of the fruit fly, as John said. The fly brain has about 140,000 neurons, okay, compared to the number that John gave you of 100 billion for the human brain. So it's much smaller. It has about 50 million synaptic connections, but it's still quite complicated. And so the place neuroscientists are at now is trying to figure out how this, dense interconnected map actually generates the behaviors that flies are capable of. And this line of research, at its ultimate goal would be to make such a map of a human brain. And it's very inspiring to hear Congresswoman Wexton speak. Imagine if we could, quickly map the brain of anyone and discover, what types of miswiring are occurring in the brain in order to develop ways to repair them. So that would be an ultimate goal. Now we're sort of in the place where we're able to build these maps of very small brains, model systems like flies or fish or mice. And in these systems, which serve as kind of a test bed, we can develop the first models that will allow us to predict function and dysfunction from these smaller maps. And so that's what I'm quite excited about. That's what I and others that I work with are delving into, and we hope it sort of sets us on that path. The last thing I would add to that is that this kind of research also has as its goal building better AI models. The models you use, like ChatGPT, they work very well, they're very impressive, but they're trained on lots of data to be able to do what they do. Yet the brains of even the simple fruit fly are way more sophisticated. Flies can even do what we call single-shot learning. They can learn something from just one example. And so we need to engineer that kind of ability and flexibility into these AI networks, and I think we can do that by learning more about biological brains, the brains of animals, and ultimately us. So I'll turn it back to you.
Thanks, Paula. That's great. So our fourth panelist is Dr. Sagi Perel, who is Director of Research at Google DeepMind. You guys might have heard about Google. It's a world-leading company in developing advanced artificial intelligence technologies. So Sagi actually started his scientific journey as a neuroscientist. Funny that, okay. As for his PhD work, he revealed how the circuits of the brain, as Lee was describing, actually control the movement of limbs, and he used that to devise a brain-computer interface in order to control artificial limbs or prosthetic limbs. So again, very much in a similar space. And this could lead to development of technologies that allow people that are paralyzed to actually feed themselves for self-feeding. So again, helping people get their lives back after injury. So his current research at Google DeepMind is focused on applying neuroscience principles to develop more powerful AI. So this is the other part of the virtuous cycle where we're going to use what we understand about how natural intelligence works to create more powerful, more flexible artificial intelligence. So Sagi, I think people would love to hear about your journey that led a neuroscientist to be directing a major research program at one of the world's leading AI companies. Now, you moved there about 10 years ago. That might have been thought of as a bit of an odd choice. People might have said, are you crazy? What are you up to? Maybe even some of your new colleagues did. So tell us from your perspective, why would a neuroscientist go into this field of AI, and what can that actually bring us that's going to be different from the conventional methods that are being used right now?
So thanks, John, and it's a pleasure to be here. So as Lee mentioned, right, everything that I'm going to tell you, what is my personal opinion. I do not represent Google DeepMind, but I think I have a lot of coworkers who share my opinion or passion of kind of applying neuroscience to improve AI. So I've always been interested in studying intelligence, right, and how intelligence works. And neuroscience studies brains, right? That's how I started. And brains are the single most example that we have of like a general intelligence, right? And what I mean by a general intelligence is something that's able to learn, right, a lot of tasks, and able to use a little bit of examples as, right, in order to kind of perform the task, right? As an illustrative example, I started teaching my son how to drive. Within an hour, he could drive a car, right? So we have self-driving cars, but we have to train the self-driving cars models for millions and millions of kind of, right, like hours of video to learn to drive. My son was able to do it in 1 hour, right? So where does the big difference in kind of learning capabilities come from? So it is important for us to understand the learning mechanism of the brain, right, and how the brain algorithms work in order to kind of bring that learning efficiency to AI models. On the other hand, AI models, right, are very, very different. They're almost kind of like an alien, right, intelligence in a way. They contain a vast amount of information, a lot more information than kind of any of us would ever have, right? But they think in a very different way compared to the brain. And for us to be able to kind of converse with them and kind of trust them, right, I think it is important to bring some aspect of natural intelligence back into AI models.
So that's great, thanks. So a couple things that both Lee and Mala glossed over was how truly sophisticated and amazing were the AI technologies that they actually developed to solve the problems. So the BrainGate group has been working for a while to develop these brain-computer interfaces for what we call brain-to-speech or brain-to-text technologies. So individuals that are paralyzed are unable to communicate, as we saw from former Congresswoman Wexton, completely there cognitively, but locked in if unable to communicate. Truly devastating and heartbreaking. And over the last 5-10 years, there have been some great successes, both from BrainGate as well as from your friendly collaborators that have generated these models. They're pretty good, maybe 70% accuracy with a small vocabulary. I think brain to text at about, 40 characters per whatever, about as well as I text on my iPhone. But recently, they had a study that with one participant, a gentleman with ALS, where your model was so good, it was literally plug and play. Can you tell us about that?
Sure. So it's part of our BrainGate consortium, which includes researchers across Mass General Hospital, Brown University, the Providence VA, University of California, Davis, Stanford, and Emory. We had a really extraordinary participant who joined us in the clinical trial, as you're mentioning, a gentleman with ALS in his mid-40s, who was losing and had nearly lost his ability to speak. As a neurologist, I refer to him as having profound dysarthria, nearly anarthria, that his wife could understand him, his care partner could understand him, but really nobody else could understand the words that he was saying because they were so slurred. He joined us in the clinical trial, and we placed sensors, we placed electrodes in a part of the brain that's important for the control of speech. We're recording the neural activity as he attempted to speak. And as you mentioned, on day one, when we provided him with a 50-word vocabulary to select from, really right out of the box, largely thanks to AI, thanks to recurrent neural networks, start to get a little lingo in here, a few language models. He was able to attempt to say those 50 high-value words, and we were able to allow him to have those words appear on the computer screen, and just as we were hearing, for those words to be heard aloud through computer-generated speech. So he got the next day off, the team did not, and said, well, we're doing okay with 50 words. Why don't we try 125,000 words? Why don't we open up the dictionary and see this extraordinary gentleman could say whatever he wanted to. So we turned on the work that day, turned on the system. He spent about another hour or so kind of training the system. So Sagi was mentioning a little bit of training so this model could understand what that neural activity meant as he was attempting to say those words. And then the first thing he said that day is this thing on? Immediately proving, A, yes, and B, his humor is fully intact, and demonstrating that. And then the next thing that he said was, I'm looking for a cheetah. Now, as somebody who thinks a lot about neural decoding, it's day 2. There's no chance that on the second day of somebody using an implanted brain-computer interface, that the second sentence that somebody spoke was, I'm looking for a cheetah. That is clearly a decoding error, and that's okay. You know, we're new at this. Except for the fact that his 4-year-old daughter had just walked into the room dressed as a cheetah. And because he was diagnosed with ALS at around the time that she was born, that was likely one of the first memories that she will have of hearing Dad's voice interacting with her in that way. This is AI, this is implanted brain-computer interfaces that are restoring discussion, restoring communication between father and daughter. When we think about impact, that's the kind of impact that this field will have between parent and child, between user of the technology and their friends and their family and their care partners and their healthcare providers and their colleagues at work. And now this extraordinary gentleman continues to use the technology over Zoom meetings to continue in his occupation. So that's one of the ways where our understanding of neuroscience, our understanding of the brain, our understanding built on decades of fundamental research has led us to this moment where we can listen to just a little bit of that brain activity, we can apply the right models, and in real time, we can begin to allow, again, somebody to communicate really just by attempting to speak.
Yeah, it's quite remarkable. And you could admit, I saw the videos of these first trials. The entire team was in tears of joy. It's really quite remarkable. Alex, can you tell us a bit about how this has impacted, your inventions, your technology has impacted the lives of your patients and how you approach their conditions?
Yes, so...
Microphone. Microphone. Yep. Or cookie.
Can you hear me? I think we all need a cookie right now. So we launched the study, the app, on the App Store in 2018. And since then, because we are crowdsourcing data from anyone in the world, so it's a citizen science model. You can download the app right now. You can learn about the study. You can consent to the study. You can become a study participant in 15 minutes. And so we call our study participants citizen scientists. So as of today, we have collected about more than 60 million key presses. And we've been able to really run a lot of traditional scientific studies based on these big data sets we acquired. But we really want this to be more than just a research tool. We want this to be a semi-consumer grade product. So on the dashboard of the app, we provide feedback information so people can use the information to learn more about their own brain, to take better control of their brain
They have
health and
control
mental
of
health.
this.
Yes, so it's agency we're talking about
Yep.
here. We want to put patients front and center in this ecosystem so that they can take better control of their brain health. So that's really our ultimate goal.
Yeah, that's amazing. So you mentioned how many people are using the app?
So in addition to the citizen science, we also have more traditional NIH-funded studies. We are actually doing a UO1 study with Stanford right now. So we have the citizen science. Over the years, we have acquired, we have enrolled about 4,000 citizen scientists.
Okay.
But we also have ongoing NIH studies where we bring people in. We
Right.
do traditional neuropsychological testing. We put them in MRI machines. We scan their connectums. So we can combine what we see in the lab and what people actually do in the natural environment.
Yeah,
And
yeah.
get a more comprehensive picture of a person.
So there's two aspects that really struck a chord with me. One is the scale. One thing I've learned in watching some of the research that we've been funding is that if you do an experiment of a certain size, you get a certain amount of information. If you increase the size of your experiment by maybe 20%, you might be lucky to get 20% more information. But there's a point at which when you scale it, you see a whole new world out there that wasn't there before. But in terms of the data we're getting, as Congressman Luttrell said, it becomes a beast that you need to tame, but actually it becomes the motivation to develop these new algorithms to get the job done. So the other piece of this is the citizen science piece, and I'm going to turn to Mala because this reconstruction of the fly brain, how many neurons?
140,000.
Only 140,000. And how many meters of axon connections?
So one thing I should make clear, you guys might hear about, brain mapping, or I'll go in an fMRI machine and get a map of my brain. Really different scale from the kind of map I'm talking about. So to make a map of the fly brain, we took electron microscopy images, 7,000 sections, millions of images, and the resolution is at the level of cells and organelles within the brain. And then we used artificial intelligence, deep learning, to reconstruct all of the neurons in that. First put the images together in a volume, then reconstruct all the neurons, reconstruct all the synapses, and make a very detailed map of every neuron and every connection. So then the question John is asking is, how much wiring, if you lay all the neurons end to end, is packed within one fruit fly's brain. This is the fly you see in your kitchen. And it's about, I know exactly, it's 150 meters, which is about a football field and a half. That was meant for Congressman Luttrell from Texas. He's not here right now, but I thought he would get that analogy. So it's remarkable, right? And so I was telling him when he was here that the human brain, actually, we don't yet have such a detailed map of a human brain, but we estimate it will be about 5,000 kilometers of wiring in a single brain. So that's about the distance from the Earth to the Moon 3 times in one person's head.
5 million. How many?
5,000 kilometers. No?
Not 5,000. Oh, 5,000? No. 5,000 kilometers?
Yeah,
That's
I
not
think
very-
so. I think that's right.
Anyway.
Oh, no, sorry. 5 million kilometers
Thank you.
in the human
Thank
brain.
you.
Yeah, sorry. I actually
Fly that much in a week, okay?
Yeah. No, 5,000 kilometers is in a mouse brain. 5 million kilometers in a human brain. So yes, thank you for the clarification.
We all slip
Yeah.
the most brilliant slip a lot of decimals.
Yeah. Okay, so yeah, it's. I think that's why these maps are difficult to make. But the deep learning technology, the artificial intelligence that helped us to make this map, that technology kind of evolved over the last 10 years during this process.
That was a
of building-
revolution.
Revolution.
It was
in
it
technology,
didn't
yeah.
evolve. It revolutionized, right?
That's right. And so it wouldn't have been possible without that.
So so when these it was 7,000, they took a brain that's the size of speck, right, a poppy seed.
Yes.
And they salami sliced it into 7,000 sections, so really tiny, tiny. And then I recall the folks who initially got that data, and they realized, so there's two steps to this. One is using AI to reconstruct it, but it's not perfect. So humans need to go in and do the proofreading. And I remember your colleagues saying, oh my gosh, it's going to take 4,000 person years of proofreading to do this with our current AI technology. And then Mala and her colleagues swooped in, and they had the better technique, which brought it down to a mere 33 years, if I understand correctly. So that's huge, 100 plus fold increase in efficiency. And then the citizen science, you employed people out there to help do the job. So it didn't take you 33 years. By employing hundreds of people, you got it down to a mere few. So this is, necessity is the mother of invention, but here it really is driving it. And again, we're now seeing this virtuous cycle where we're learning how these circuits process information, and we're using that to devise better techniques. So it's amazing what you folks did, because you took an impossible problem and you solved it, right, through these different kinds of techniques. It's not evolved. It's not revolved. I don't know what the right word is. But it's really quite something. So, Sagi, how have you seen this? You know, from what you can tell us, because I know you work at Google DeepMind. How have you seen? You know, where have you seen the revolutions? Where's the revolution going to go? In what direction? How is it going to solve some of these problems? How can we? I mean, God forbid we have more self-driving cars, but how can we make it so that they can train more quickly, more reliably, based on less data, like your son or my daughter learning how to drive?
Yeah. So, I mean, thinking about kind of, the two different kind of intelligences that I talked about, right? The brain versus kind of AI. So when you think about the brain, the brain. Okay. So talking about this with kind of AI researchers, I think oftentimes I get kind of like a stare of like, what are you talking about? But I mean, like, so when we talk about biological brains study in a very different way compared to artificial brains, right? I think it kind of like, the disconnect kind of like between the two, as the congressman was mentioned, was kind of like AI models of today are kind of based of neuroscience understanding of maybe the 1940s or 50s, right? And our kind of understanding of how the learning happens in the brain has evolved a lot since then. So we use kind of, some form of what we call Hebbian learning, right? Like meaning that if you could take an artificial network and you present it with some input and some output, then the neurons in the artificial network learn to change their connections kind of slowly based on the relationship between the input and output, which is very similar to what the brain does. But we don't understand the exact mechanism by which the brain does it. So we have a different algorithm in artificial intelligence. It's called, a gradient descent. It's kind of like a mathematical approximation of that. But kind of like the difference in scale is that the brain can learn from one-shot examples, right, or like a few examples, whereas the artificial networks need a lot more data. So if you think about acquiring a language, right, they need to read a lot of documentation, right, maybe all of the text documents in the internet to kind of like understand the meaning of words and sentences that kind of connect them together. And when you look at brains, children learn kind of like language maybe over the course of a few years, but kind of like very, very quickly and form connections between them that are very different. So by basically, right, by investing in like a neuroscience research, right, that looks more on the side of how do the brain learning algorithms work, right, what kind of like distill out of it into kind of, the machine learning algorithms, right, like maybe thinking forward, if you want to take an AI model out into the world and put it into, right, a robot, for example, then the robot needs to look at a lot of visual data, right, a lot of kind of like auditory data, sensory data, and kind of fuse it all, together, which is something that our brain does well. And the brain kind of knows what information we should retain in memory, right, and what information we should keep for later, right, and how to make decisions. All of that are kind of like pieces that are missing in current AI, right? So if you think about how to project it to the future, those are kind of like, some of the big missing pieces in AI today, right? that we need to distill out of kind of neuroscience understanding.
So this basic understanding is what's going to push it forward. So Mala, maybe you can talk a bit about how actually the origins of AI actually come from neuroscience, from your former colleague, or your colleague, John Hopfield.
Oh, yeah. Many of you might know that last year in 2024, the Nobel Prize in Physics actually was awarded for foundations in artificial intelligence. And one of the prizes went to my colleague, John Hopfield, who's now an emeritus professor, who was working then, several decades ago, on just basic neural mechanisms of memory. His problem was, how does the brain store memory? How do groups of neurons actually form a memory? It's a great question. And he thought, it would be interesting to form kind of artificial networks. Just like the brain is neurons and synaptic connections, artificial networks are nodes and connections. So to make an artificial network that could store memory. And by doing this basic research, he contributed, or he, was foundational in this line of research that eventually led to the artificial intelligence networks we have now. And one thing I find interesting about that, it was so fun to celebrate this prize with him last year, but it was exciting to hear the story about how curiosity drove his research. And so the question he had in mind about memory, just a very basic question, and often neuroscientists are, they pick these kind of fundamental questions, something fundamental about the brain that they want to solve, and don't know what the application will be decades down the road. It's often hard to see that. And so the kind of support and funding we get for answering these basic questions can really pay off down the road in ways that are hard to predict. Yeah.
Yeah, so this brings up an interesting conversation that we've been having a lot lately, which is not just the role of foundational basic research, where the curiosity is driving the questions that are being answered in unique ways, but where should the work be done and who should fund it? And it's a very rich ecosystem, as I think you can see. We have just four panelists who represent different walks of life, and believe me, there are many, many more perspectives as well. But I'd love to hear from you folks, just in an open forum, about the different role that funding plays, funders play in this continuum from basic understanding, basic foundational mechanisms through translation, and then through what we call reverse translation back again. So Lee, you've had quite a bit of experience in this brain-computer interface space. I mean, tell us about the journey of your inventions, your group's inventions, and what's it going to take to get it out to people, and how are we doing in terms of the progress of actually getting these inventions, these devices, to help people on a more regular basis?
Yeah, so when I think about the beginnings of this field, I think back to the neural prosthesis program. I think quickly back to the 1960s, the 1970s, the original laboratories of motor control at the NIH that were asking fundamental questions. How does the brain create movement? How do we record from a whole bunch of neurons in the human brain at the same time? How can we interpret that brain activity? And this is work that was sponsored by the National Institutes of Health, by the Department of Veterans Affairs, by a number of federal agencies. And even though it was fundamental research, part of the interest was, well, if we can understand this well enough, then maybe we're going to get to the point that one day in the future, we're going to take those data, we're going to understand how that part of the brain works well enough that we're going to be able to restore a lost neurologic function. And it was exactly the result of those decades of fundamental investment that led to the next stage of this, which was academics, our own and the BrainGate Initiative and others, trying to take these data and doing the first of these clinical trials that would show it was possible to restore communication for somebody who perhaps is the result of a brainstem stroke. I'm looking at Natalia, who is the president of the American Academy of Neurology. She and I, we've known each other for, I won't say how long, for a while. We've both taken care of people who yesterday were able to move and to speak without any difficulty, but today suddenly have lost that ability. For people with ALS who are progressively losing the ability to move or to speak. If it's the next stage, that academic consortium, those academic groups showed it was possible to restore some of these functions. But if I take my scientist hat off for a moment, put my physician hat back on, what I really want, and what I wanted this past weekend when I was in the neuro ICU, is to say, okay, here's a patient. This patient needs this device. And the final stage of that translation is not in academia. We don't create in academia the final stage of an implanted medical device. That is a job for industry. Industry takes the best of the academic research that's happened, they harden it to a product, and then they go through the process of testing it, further developing it, and hopefully demonstrating that it's both safe and effective for human use to help people with neurologic disease or injury. And that translation is working exactly the way it's supposed to. Academic groups showing what's possible, and just in the past 8 to 10 years, there are now more than a half dozen companies with collectively, according to a generative AI search, more than $9 billion in valuation that have really, and they only exist because of that fundamental investment that we collectively made to make it possible to de-risk the science for these companies to now create devices that we all hope are going to restore communication and mobility. So I've been able to see that translation happen exactly the way that it's supposed to, and that really hopeful return on investment that's turning into reality.
Yeah, just in the last few years, we've seen a couple of startups that sprouted out of these technologies that we help support to get there. So I think, yes, I think federal funding is critical, but we're only just one player in the ecosystem. An ecosystem only thrives if the different players are healthy and doing their thing. And so, Guy, I mean, again, you started out in the space of neuroprosthesis, understanding what we call motor control. How do you see this evolution, this initial discovery, de-risking, and then application phase?
So actually, want to kind of like highlight maybe a slightly different angle here, right?
Yep.
I mean, like talking about the role of academia or the role of federal funding, right, like versus industry. I spent half of my academic life in neuroscience, half of the academic life in kind of AI research, and I can talk to neuroscientists, I can read neuroscience papers, I can talk to AI researchers, I can read AI research papers, but as the congressman was mentioning, there's kind of a wall, kind of a disconnect between the disciplines. If you give a neuroscience paper to an AI researcher, most chances are they won't quickly enough gather what they need out of it or have an interest of reading it. There are too many biological details, right? So I think the role of academia and federal funding, could be grow the next generation of researchers, right, that are actually well versed in both disciplines and can actually serve as a bridge, right? They kind of bring the best of neuroscience research. It takes maybe 5 or 10 years to kind of come to fruition into industry. And in industry, it might be kind of like a timeline of 1 or 2 years, right, to kind of develop it into a product and launch it. So the timelines are very different, but I think you need the collaboration and kind of the spectrum from the basic research as like long-term, right, into the shorter term, I think kind of industry that's very product oriented, right, a lot of times.
Yeah, for sure.
Could I add one thing to that?
Absolutely.
I think, one thing that federal funding has been great for are these very long-term projects, and our fly map is just one example of that. It actually took 10 years to go from sectioning the fly brain to publishing the map, and it involved, as John said, that the technology really changed during that time, which made it possible to do this. But it also involved a very large international collaboration. People from universities all over the U.S. participating, and we had this open science effort where we decided, and the NIH encouraged us to make the data available as soon as we had it. So we had those first images of the fly brain. And while we were correcting the AI-assisted reconstructions, we opened it up and asked people in the community to help us. And so by helping us, it shortened the time to delivering the map, but it also fueled their science. They started to use the data for their own scientific questions. And now there are dozens of papers already, even though the map was just published last year, that have already used used this map for scientific understanding and discovery. And I think that's the kind of thing these long timescale projects and funding for them can do. And I would say that if that funding had been in jeopardy at all over that 10-year period, we couldn't have just picked up again and produced this map later, because once you kind of turn the spigot off, it's very hard to turn it back on again.
So Alex, you kind of,
Did you want to say something?
yeah.
Sure, I can say something.
Yeah.
So, in addition to very generous NIH support we have over the years, we also benefit from partnerships with nonprofit organizations. For example, we work with Sage Bionetworks and more recently Global Research and Imaging Platform, and they built the underlying backend infrastructure for our smartphone app. So without this partnership, our research study wouldn't be even possible.
Yeah, and Alex, when you're talking about your app, you mentioned and how it's being used by the folks using it, you mentioned this really interesting word of agency. And that gets to, with any new technology, it can open doors that may lead us to places that might look a little bit scary to people. But, I know that you've been considering this. I know that in the BrainGate Consortium has been considering this. But you want to talk a little bit about how you think about how to develop these technologies in a way that will help people and mitigate any potential harms?
Yes, this is actually my most passionate topic. So thank you for asking me to speak about this. So I think today a lot of the discussions about artificial intelligence is about productivity and task automation. But as a practicing psychiatrist, I believe that artificial intelligence should always be in the service of natural intelligence. So there is this contrast I see, and that's agentic AI versus human agency. It seems like every company is making agentic AI right now. It's a buzzword. So what does it mean? It means that it's an autonomous AI system that can take a wide range of actions and interact with humans in the virtual world, or more increasingly in the physical world. And I think we should never sacrifice human agency as we develop agentic AI. And I'll give you an example of what I mean by that. So I take my piano career very seriously, although it's non-existent. I derive meaning from my struggles at the piano. So what that means is that it is irrelevant if an AI agent can play the piano better than I do. But I'll be very happy if AI can make me become a better pianist. So that's human agency. It's about self-realization. It's about finding personal meaning. And for me, it's playing the piano. For you, it's going to be something different, arts and crafts, cooking, or drawing.
Yeah, I appreciate that. And again, it's what these new technologies, whatever they are, what they can do for us to make our lives richer and fuller. So I think we're coming up on time. I want to leave a few minutes if anybody has any questions. I know we're getting up onto the half hour. And again, I think the three take-home messages that I hope you will bring away today are really understanding the vast complexities of the brain, from the fruit fly brain all the way up to human brains, really will drive the invention of unbelievably powerful new technologies. I'm a Pollyanna. We saw it literally over the last few years as well. And these new technologies, in turn, are going to drive better ways of taking care of humans. And then, as you walk around everyday life, just know that whatever's going on between your ears is far more powerful, far more flexible. You can learn things far more quickly than these humongously complex, no offense to your colleagues, AI technologies that are out there. And that's what we need to tap in to drive better AI technologies so they can work even better for us. So it's this virtuous cycle of learning more about the brain in order that we can design better artificial intelligence. So with that, I want to thank our panelists.